Hello, this is Nat and this is another MAT video. Today we're now going to tackle question 6 of 2019. If you remember the first episode of season 2 of MAT, I'm very interested in obscure numeral systems, so this question is for me. Before we start, let us explore these two very long paragraphs. Firstly, the term flexidecimal is incorrect. The correct term is factorial base. Let me explain why. To explain why, we had to do part 1 first. So, write the numbers from 5 to 13 in what they call flexidecimal, but what is actually called factorial base. So, we have 0, 1, 2, 3, 4, and then we can have 5, but 6 needs another digit because 30 is not okay in what is called factorial base. Then 6, 7, 8, 9, 10, 11, and now 12, we can have a 2 here because since 2 is allowed in the second place, we can have it in the third place. 200, which is 12, and 201, 13. There. Want to know why it's called factorial base? It's because the first digit can have either 0 or 1. Then it can have 0, 1, 2. 0, 1, 2, 3. If you count the number of permutations you get in these digits, you will have 2 for single digit numbers, 6 for 2 digit numbers, and 24 for 3 digit numbers. And these numbers are the factorials n plus 1 factorial, where you count from this. So this will be called place 1, and this will be place 2, and this will be place 3, and so on. That's why it's called factorial base. So describe a workable procedure for converting factorial base numbers to decimal and explain why it works. Don't worry. So I can convert 1, 2, 2, 1 from factorial to decimal. Okay, look. Here, this has value 1, this has value 2, this has value 6, and this has value 24. So 24 plus 2 times 6 plus 2 times 2 plus 1 equals to 24 plus 12 plus 4 plus 1 equals to 41. There. Describe a workable procedure for converting decimal numbers to factorial, or we'll call this base f. So we'll write 210 equals to 10f, f for factorial. So this is our convention we're now going to use. We could describe a workable procedure for converting decimal numbers to flex. So we're going to have 255 to factorial, although flex is a cooler name for this one, but I'm going to use factorial because that's the widely known term. 255. So what is the largest factorial which is less than 255? 120. So we subtract to get 135, 120, 15, and then what's the largest factorial here? 6. And then 9, 6, 3, 2, 1, 1. There. So our 120's place is, I'm going to write 120, 24, 6, 2, 1. How many ones do we have? We have 1, 1, 1, 2, 2 6's, and 2 120's. Since there are no 24's, we write a 0 in here. So there you have it. 255 in decimal is 20,211 in factorial base. We could add factorial base numbers by converting them to decimal, adding the decimal numbers and converting the result back again. This is a very unwieldy procedure. So we're gonna do them in factorial. Yep. So 1221 plus 201. Since it's like an ascending base here, this is like base 2. So we're doing base 2 addition right here. 1 plus 1 is 10 in base 2, and 1 plus 2 in base 3 is also 10. And then 1 plus 2 in base 4 is 11. And then so we now have the number 2100 in factorial. Yay! Given a flexidecimal number, how can you test whether it's a multiple of 3 without converting to decimal? Now this is a very difficult one. So we're going to look at our list of factorial based numbers here. And we're gonna... my mouse. Wait, so we have 0, 1, 2, 3. We're gonna circle multiples of 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So as you can see, the multiples of 3 either end in 1, 1 or 0, 0. So let's write this down. Forget it. The multiples of 3 end in either 0, 0 or 1, 1. There! That's a very simple reason, and it's called divisibility test. So basically, this is like our 8 or 4 or 2 divisibility test in base 10. But this time in factorial, divisibility tests are much more fun because you only had to check the last few digits. No fancy summing up like you do with 3 and 9 decimal and 11 in decimal, or 3 and 5 in hex. Because it's a computer science paper, so I'm mentioning hex. Alright, so if the 100,000 arrangements on the letters A, B, C, D, E, F are listed in alphabetical order, what arrangement appears in position 3, 4, 1, or 1 in this list? So firstly, we're going to move this question down so that I can see it better. And secondly, what we're going to do is that we're going to write down A, B, C, D, E, F. Now we're going to label our list 0, 1, 2, 3, 4, 5. And then we now have the number 3, 4, 1, 0, 1, factorial base. Right. So the first letter we have is 3. So what we're going to do is that we're going to write D and then cross D out. So D is out, the 3 is out. Then we have to cancel and change these numbers. And then because the ordinal has changed and we can't use 4 or 5, so we replace it with 3 or 4. Then we have 4, so it's F. Then we delete 4, and then we have 0, 1, 2, 3, and then 1. So B, delete this, and then delete the 1, 2 is E, and then 0 is A, 1 is E, and then the last one we have, which is marked as 0, since we have no more, so we just put C at the end. So there you have it, converting a factorial based number into a permutation. And coincidentally, factorial is also one of the best number bases to learn, because the irrational number E in what is factorial base. So basically, conventional factorial base has 1, 1, 2, 6, 24, 120. And then we're going to have our decimal factorials, or factorimals, whatever you call them. And so we're going to denote them, and then you put 1 over 1, 1 over 2, 1 over 6, 1 over 24, 1 over 120. And this is great, because I don't know the expansion of pi and factorial yet, but I do know the expansion of E. And it's a very simple expansion. Get ready for this one. 1.11111111, or 1.1 recurring. In general, any number which is a repeating sum of factorials like E, or its cousin 1 over E, or sine, cos, sine, tan, cot. I don't know about pi, but yeah, I basically don't know about the behavior of factorimals. And so there, we're done. See you.